Today's notes are on nonlinear models. This is section 3-6 in your textbook. Now we've talked about linear and quadratic models. So if we look at a graph, for example, of a linear model follows a general straight line pattern. If we look at a graph of a quadratic model, it follows a quadratic pattern. It looks like a parabola. Now there's a bunch of other ones on here that we need to address because a lot of times in nature we don't have these nice lines or nice smooth parabolas, but a lot of times we'll see data follow exponential models, which have this slow initial growth but then shoot up pretty quickly. Logarithmic models are the inverse of those exponential models, so we'll see them rise pretty quickly and then level off. A few we haven't talked about, logistic models. Logistic models look like an exponential to start, but then level off up here. Gaussian, if you're taking statistics, you might recognize the bell-shaped curve. That's a Gaussian model. And a power model looks kind of exponential, but usually we don't see that extreme growth that we see in an exponential model. Okay, so those are some general shapes. Now, they don't have to follow these exact shapes, but general shapes of different kind of models that we might encounter, excuse me. So let's take a look at an example right away. This example says, what type of model should you use for the following data? So what we want to do first is graph this data and see, does this fit a line, a parabola? What kind of curve does this fit? So I'm going to let my calculator do a lot of this work for me. So let me put my notes aside and grab my calculator. Oh, there it is. And remember, first thing we want to do is press our stat key and then enter to put this data into two lists. We're going to put the x's into list 1 and the y's into list 2. I've already got them in there, so now we can take a look at some different regression equations. Now one thing you can do, you might not need to do this, but I'm going to look at a stat plot. Second stat plot menu. I'm going to set up the first stat plot, so it's a scatter plot comparing list 1 and list 2. And if we zoom in on our statistics, we'll see a graph of this data. And that graph might help us determine what kind of shape this is. And I think you'll agree it's not going to be a linear function. It's going to be one of those curves, maybe exponential, could even be quadratic. Now, how are we going to find out which one? Well, I'm going to press my stat key and I'm going to go to calculate. And we have all these different regressions in here. So for example, we could find the equation of the line of best fit. And I'm going to do that to start. I'm going to press enter. Linear regression of the data. Now my data is in list 1 and list 2, so I can save time by just pressing enter again. And it tells me the equation of the line of best fit. Now on your calculator, it might tell you something more. What we're looking for is what's called the correlation coefficient. We're looking for an R value. And I need to set my calculator up so it'll show that. So if I press the second key and then 0, it gives me a catalog of all the different functions my calculator will do. And what I'm looking for, I'm going to scroll down till I see a function that says diagnostic on. Now this is something you only have to do once. Once you do this, so now that I've done this once, it's done. I never have to do this again. But now, if I do one of those regression functions, it not only gives me the equation of the line, it also gives me this R value down here. And notice my R value is negative 0.95. So for linear regression, negative 0.95. Now the closer R is to 1 or negative 1, the better the fit. So I'm going to go back here and I'm going to calculate the quadratic regression. And since my data is in list 1 and list 2, I can simply press enter. And here, well, we don't have an R value, and actually R only applies for linear functions, but we have an R squared value. Notice the R squared value is equal to 0.99. Up here is 0.91. So quadratic regression fits much better. I'm going to try some of these other ones. So if I go to calc, I can see there's a cubic regression, a quartic regression. I'm just going to look for the ones on the previous page. We have another linear regression, natural logarithmic, exponential. So let's try these two. Natural logarithmic regression. And that gives me an r squared value of 0.999. That's pretty good. That's pretty good. Well, let me try another one. So if I scroll down a little further, I will see an exponential regression. And again, my data is in list 1, list 2. I'm just going to press enter. Here we get an r squared value of 0.94. So pretty good, but not the best fit. So for each one of these, we can find a different model. I'm going to try, I think there's one more in here that was on the previous page. So we had linear, quadratic. We haven't talked about cubic and quartic, so let's just skip those. Logarithmic, exponential, and power regression. There's also logistic, I guess I could do that, and sign regression. And manual fit, we won't worry about that. So I still need to do this power regression. There, my r squared is 0.996. That's pretty good. And there was one more in there that was on the previous page, and that was logistic. And that's taking a little, oh, it didn't like that one. Okay, I guess I'm not going to do the logistic regression. Okay, but either way, I'm going to just put my calculator aside for now. And the one that has the best fit was this logarithmic with an r squared value of 0.999. So that tells me that the best fitting equation through this data is going to be y equals, it says a plus b times the natural logarithm of x. And it gives me values of a and b. So y equals 31.9 plus negative 5.8 times the natural log of x. Okay, so there's the best fitting curve through this data. If we graph that, it would come really, really close. In fact, with an r-squared value of 0.999, it's going to come very close to hitting all those points. All right, let's try that again. So it says on the second example, fit the data from example 1 to logarithmic and linear models. And actually, I already did that. Logarithmic and linear, compare r-squared, determine the best fit. So let me go back. Logarithmic was this one right here. Linear was this one right here. They both have a pretty good fit. R squared here is 0.91. R squared here is 0.99. Both have a pretty good fit, but that logarithmic model is a much better fit. Okay, so that example is taken care of. Let's take care of this third example. Find the model that best fits the data, then predict. So now that we've got a model, we want to make a prediction. We want to plug this into the model. So we're going to need to do the same thing we did before. We need to put this data into two lists of our calculator. Once it's in there, we need to calculate a number of different regression models and pick the one that fits the best. So I'm going to put this data aside once again and grab my calculator. There it is. Just like before, I'm going to press the stat key and hit enter. And we need to put this data into list 1 and list 2. I've already got it in there. So once it's in there, then we can press our stat key. We can calculate, and we're going to just try all these different regression models. So let's start with linear regression. The convenient thing, if your data is in list 1 and list 2, you do not have to type those lists in there. And that gives me an r-squared value of 0.978. That's pretty good. So now I'm going to calculate a quadratic regression. That gives me an r-squared value of 0.998. That's even better. Let's keep calculating. So now I'm going to calculate, skip that cubic and quartic because we haven't talked about those yet. Those might give better fits, but we won't encounter those. Logarithmic gives me an r-squared of 0.93, so that's not going to be the best. Let's try, I believe exponential is the next one on the list. And that gives me an r-squared of 0.991. That's really good, but not the best that we've seen. So let's keep calculating. Let's try this power regression. Gives me an r-squared of 0.997. So the highest r-squared value, and I'm not even going to try logistic here, the highest r-squared value is This one here, this quadratic regression, gives us the best r squared value. Okay, r squared there is 0.998. So our equation then is going to be y equals ax squared plus bx plus c. And we're going to plug, let's see here, it says predict the kinetic energy if the speed is 3 meters per second. So we first need a, b, and c. So the kinetic energy is going to be equal to about 0.023 x squared plus negative 0.013 x plus 0.008. Now, just a warning for you. Sometimes you get answers that don't make sense unless you use a whole lot of decimal places. So we're going to plug 3 in place of x and see what happens here. So I'm going to say 0.023 times 3 squared minus 0.013 times 3 plus 0.008. And we get an answer of about 0.176. Yeah, that seems to fit. So if the speed is 3, we get 0.176. If you get an answer here that doesn't fit the data, it means we just need some more decimal places with all of our coefficients. Okay, so that's how to find different models. That's how to find our correlation coefficient. We need to practice that a little bit, so get some practice done on page 242, please. See what you can do on these, and let me know what questions you have on any of this.